Hi, this is Jack from TritiumSoft.com talking to you today about BulletCalc3. Let's get started. So, in the last video for BulletCalc3, we were talking about the general relationship between the size and speed of a projectile and its maximum range. And we were using the analogy of a battleship shooting a cannon versus a shotgun shooting a pellet. And the way to think about it is you know that that battleship can shoot many miles and that a shotgun shoots very close distances. And the primary reason is because of the size of the projectile and the function that it has with the aerodynamics. And so you get these small pellet. The aerodynamic drag is a much larger percentage for the small projectile than it is for the overall energy as it is for the battleship shooting a shell at another ship miles away. And so what that means is small things lose energy from air resistance quickly because for a couple of reasons. One reason is because they can't store as much energy. When you have something very small, it's very light. The amount of energy it has to lose before the velocity starts falling to zero is a lot less than a very heavy projectile compared to the air resistance it faces. And so that's just a general rule, just a general way of thinking about it. We're not talking in terms of pure scientific equation here, but that's just the general trend is the smaller projectiles lose their energy much quicker due to air resistance than a big heavy shell coming out of a battleship. So the other thing we were going to talk about here is this drag coefficient. So you can see the drag coefficient here. I've included prevention from accidentally putting in the wrong value. And the reason I did that is because I would put in the wrong value. And so for instance, instead of saying 0.3, I might just say 3. And the problem with 3 is it's pretty much an impossible drag coefficient. So if I press that, you can see the program corrected it to 0.3. Not that that's the correct one, but that it's more correct than me putting in a 3. And the reason for this is because if we go back out here to Safari, we can see NASA publishes these shape effects on drag, and you can see there's nothing on this list that approximates a 3. A flat plate, which is very unaerodynamic compared to that flow from left to right, is 1.28. So, and a bullet is 0.3. And so having a value of 3, what happens is that's a tremendous amount of drag, and it messes up all your equations. So that's why I've included that feature that to help you get the decimal point correct. If you get it wrong, it'll correct to some degree. And the other one here is we want to talk about the effect of the shock wave. And so one of the problems that all of these ballistic calculators face is that we have a shock wave. And if you look at down here, I included pictures of shock wave. So if you've seen the movie The Right Stuff, in that there's some depiction of the Bell aircraft where they broke the sound barrier and all the issues they had with control. And these issues have to do with this shock wave phenomena that happens that creates this sonic boom, right? So the sonic boom is around 700 miles an hour, and it depends on what kind of medium you're in, but in general, we have the speed of sound, and we have these shockwave developing. And the problem these calculators have is that the shockwave interferes with the flow of air around the projectile to the point where it becomes an unstable calculation. And you also have the phenomena of tumbling. So on some of them you can have tumbling. On other issues with the right around the speed of sound. And you have to remember with a bullet, it's going slower and slower as it travels. So you might start out at Mach 3, but depending on where the target is, your ND, it's eventually going to go 0. And so you're going to pass through these sound barriers. And when you're passing through, they can have effects based off of the flow being disrupted by the phenomena of the shock wave collapsing or becoming unstable. And so if you want to read more about that, we have Sonic Boom on the Air Force here. They have a really nice page, the Air Force, on sonic booms. And we have Shockwave on Wikipedia. And the best one I found, though, was on Quora. On Quora, we have somebody who has a PhD, Mr. Kim Aaron, PhD from Caltech. That's a pretty highfalutin school there. His answer is extremely easy to understand, and this illustrates, if you look at this Mach number versus the coefficient, the drag coefficient, you can see there's spiking around Mach 1, and that's what we were talking about, is that all of these calculator programs have to deal with this phenomena of not having a nice linear experience over these speeds. And because the bullet is going to travel from Mach 3 to 0, it's going to pass through this big mountainous peak here around Mach 1. And so that's the question of what to do about that. And so some of these modern ones incorporate other schemes for dealing with this. But in BulletCalc3, the way that we've dealt with it is a more simplistic model, an older model, but it's one that is easier to understand and can easily be adjusted without having adverse effects. And so in some ways, what we're doing is we're smoothing out what other programs might try to use other data to fix. And so if we go back in here, BulletCalc3 is simply taking the drag and deleting, it's subtracting the loss in energy over time. So it's repeatedly going through and calculating what these energies are, and it's subtracting out what was lost through drag to give you a good result. And the way we deal with that is, part of it is experimental, such as in we shoot the gun, we see what happens. But the other part is to estimate. So if I want to say, well, what, ballpark figure, what is this round going to do? I can do it with BulletCalc3. But if I want to make it better, I have to see what actually happened and what's useful, or I have to find data such as in this Winchester box. We have a Winchester box here. They have a ballistic table here. And so there's a few different strategies, but in general, though, you can get a really good sense of what a round can do. So for instance, if I go down here and I want to take a 50 BMG. So 50 BMG it's not just a machine gun round, but it's also a sniper rifle. So for instance, Barrett. And so we're saying that it's coming out the barrel 2820 foot per second, right? 2,800 feet per second, very fast, and it's a big, heavy bullet, 750 grains. That is a big bullet. If you ever seen 50 BMG, a box of 5 is like $100. And so if you look at the yards, here we put in about 2,000 yards. And if we look at the caliber, it's 0.51. And we have a drag coefficient of 0.11. So if we want to affect the program, we can adjust this drag coefficient, but I went through on this one and it's pretty solid. And so the first thing you see down here is this is our distance to target at about 2,000 yards. And you can see, you know, how long it took to get there, almost 2.5 seconds. And the bullet drop about 100 feet. And so what that means is, I mean, in terms of the angle, it's not that much because this is 3,000 yards. But it's still 98 feet drop from, and that's why they have the clicks up there on the scope. But then we can also see at 100 yards, 200 yards, 300 yards, 400 yards, 500 yards, and 1,000 yards. And so at 1,000 yards, we can see our bullet speed in terms of Mach number still at 2.12, whereas if we're at 2,000 yards, we're down to 1.8 for our Mach number. And so this calculator is very useful for modeling bullets and bullet energies. You can see this is why this is a very dangerous round, is the bullet energy at 2,000 yards is extremely high, 10,000 joules, 6,900 foot-pounds. It's tremendous. And you're talking, this is at a mile out. So I hope you enjoyed this video. See you in the next one.